All right, so this is part A of separations homework 4. This is graph the total number of degrees of freedom for a total condenser, a partial reabsorber, liquid splitter with heat exchanger, vapor liquid equilibrium stage with heat exchanger, so all the way down to G. So we'll get started and we'll do total condenser. Actually, let me here. This open. So this is our distillation column. We have our rectifying section, we have our stripping section, we have our feed, and then we have our partial reboiler, our total condenser, our splitter. And we're looking for the degrees of freedom. So the degrees of freedom is our number of unknowns. Go ahead and pull this up. So our number of unknowns minus our number of equations and slash or number of relations. So this goes all the way back to MEB. Usually that number is positive. If it's, or like when you're approaching these kind of problems, usually it's positive. You want to find some kind of extra relationship or some kind of extra equation that sets our degrees of freedom to 0. And if it is anything less than 0, then your system's overspecified and you can't solve it. But let's go ahead and do our condenser. So that's going to be this section up here. So that consists of an inlet stream, our condenser, and then an outlet stream. So let's start with unknowns. We'll have our equations over here. So we have two streams. And each stream is going to have C number of compositions, so those are unknown. And then they're also going to have two unknowns in the form of temperature and pressure. And then for our system, we have 3 additional unknowns of our heating element, or I guess our cooling element in this situation, temperature and pressure. So that gives us 2 times C, now that's bothering me, 2 times C plus 2 plus 3, and that gives us 2C plus 7. So then for our equations, we have C number of mass balance equations, we have 1 energy balance equation, and then an assumption that we're going to make is that everything that immediately leaves the system has the same thermodynamic properties of what was in the system. Kind of like how when we dealt with the mixed flow reactor in process dynamics homework 2, we assumed that the concentration of the substance coming out was the same as what was in the mixer because it was so well mixed. So we're going to have the relationship of T in and T out and P out. And that's going to give us, or I guess we're going to have two relationships. So that's something useful. For every outlet stream that any system has, we're going to be able to apply that relationship. So then we have 2C plus 7, and then it's going to be minus C plus 3. That's going to leave us with C plus 4 degrees of freedom. All right, so let's go to the partial reboiler. So for this one, we have an outlet stream. No, we have two outlet streams, one inlet stream, and then a system that has heating element, temperature, and pressure. So kind of the same deal. 3 streams. C number of compositions in each stream. And then each composition also has 2 temperature and pressure variables. And then we have 3 system unknowns, which are Q, T, and P. So that gives us 3 times C plus 2 plus 3, which gives us 3C plus 6 plus 3, which gives us 3C plus 9. Then for our equations, similar deal to what we just did. So C number of mass balance equations. We have 1 energy balance. We have 2 times, so we have 2 outlet streams, so we have that outlet temperature and pressure relationship twice. And then we have C number of equilibrium equations throughout, since this is going to equilibrium. So that leaves us with 2C plus 5. Subtract this from that. That leaves us with C plus 4. All right. Now for our splitter, we'll fold this over. So for our splitter, you have something like this. Temperature and pressure, inlet stream and an outlet stream. So we have 3 streams. Again, each of them has C number of compositions. Another 2 unknowns in the form of their temperature and pressure. And then an additional unknown in the form of their flow rate. So that's something new being introduced in the splitter. And then we have, I can't remember if we have a heating element. I don't think we have a heating element in this one. So we have 2 T and P of the system. All right. So then for our equations, we have C number of mass balances, 1 energy balance, we have 2 times 2 T out, T out relationships. And then we know So we have 3C plus 3 plus 2, 3C plus 9 plus 2, 3C 11. I can't remember if this is going to equilibrium right now. So let me check that and I'll be right back. All right. So it is going to equilibrium. So we have C number of equilibrium equations. And there also is a heating element. So that's 3 unknowns in the form of QTP, which bumps this up to 12. And we have one more relationship, or I guess two more, which is the mole composition, because we know that these two outlet streams share the same molar composition. So we're left with 2C plus 7. So subtract this. That leaves us with C plus 5. Let's do which one's next? Vapor. Oh yeah, there was the heat exchange. I didn't even see that. Vapor liquid equilibrium stage with heat exchange. Okay, so then this is just a normal equilibrium stage. So we have 4 streams. Each of them has their composition, and then an extra 2 unknowns in the form of T and P. And then we have the 3 unknowns of the system, which are Q, T, and P. And then we have our equations. Actually, let me go ahead and write out 4C plus 2 plus 3. So that gives us 4C plus 8 plus 3, 4C plus 11. Okay, then for our equations, we have C number of mass balance equations, C number of equilibrium relationships, or equilibrium equations in the form of Raoult's law. We have 2 outlet streams, so that's going to give us 4 relationships in the form of T out and P out. And then 1 energy balance. Have 4C plus 11 minus 2C plus 5. And that gives us 2C plus 6. And then we have vapor liquid equilibrium stage with feed. Okay, with feed. So that's going to be the same thing. So everything holds up, except we also have the feed stage. So that's just one more stage. So that's going to be an extra C plus 2. So that's going to be 2C plus 6 plus C plus 2, which comes out to 3C plus 8. Okay, so for next one is a series of equilibrium stages. So I guess in this example, we'll have 4. And each equilibrium stage has the degrees of freedom of 2c plus 6. So let's say that we don't know how many stages we have. We're just going to notate that as n. So we would have 2 or n times 2c plus 6. But one thing that we can account for is all of these streams are doubled up. I wouldn't necessarily call it an equation, but it's unknowns that we can remove since they're technically showing up twice. We only really have one equation, and that's our number of stages. But if these are our unknowns, our equations is just 1. Then we can subtract from our unknowns. Get rid of c plus 2 for any repeating stage, or for any repeating stream. So the number of repeating streams that we're going to have are going to be, I guess, let's look at this example. So we have 4 equilibrium stages. We have 1, 2, 3. We have 3 sets of repeating streams. So that's going to follow 2, and then we would have 3 in here. But we're going to have the format of n minus 1. So if we had 5 in this example, then we would have 4 sets of repeating streams. If we had 6, then we would have 5 sets, so on and so on. So yeah, those are unknowns that we can get rid of. So we have 2nc plus 6n minus 2 times nc plus 2n minus c minus 2 minus 1 out here. So then we have 2nc plus 6n minus 2nc plus 4n minus 2c plus 2c plus 4 minus 1. Okay, so it's going to be 2 NC's die. This is a minus 4n. So 2n plus 2c plus 3. General form for a set of equilibrium stages in series. All right. So just to start off, I misspoke right here. This actually isn't an equation, it's an additional unknown. So that needs to be a plus 1, which means this is plus 5. So let's look at our total, our entire system. So we'll add all these up. So that gives us 1, 2, 3, 6, so 10C. Yeah, 1, 2, 3, 6, yeah, 10C, and then 2 NR plus N5. Also, sorry, I didn't preface what any of this was. These are all the degrees of freedom of our individual components. And then a rectifying and stripping section, that's pretty much what we found from when we did individual, or no, when we did a set of individual equilibrium stages. Um, but we have to specify that they're two different sets. And then plus, oh gosh, 8, 13, 21, and then 31. I did my math right. 16, 20, okay, 31. All right. However, kind of like we did when we were looking at the sets of equilibrium stages in series, we have to look at any repeating streams that we have. So we have 1, 2, 3, 4, 5, 6, 7, 8, and 9. So that gives us minus 9 times c plus 2. So then that gives us 2nr plus 5, or oh gosh, 2nr plus ns c plus 2. So then 18 is 13. It's just a C on the outside. All right, so these are our degrees of freedom. But we're going to go ahead and state a few things. So we're going to state that we know all of the, aside from the partial reboiler and the condenser, we know all the Q's and all the P's. So that's going to be, so that's going to give us two unknowns, or that's going to give us two knowns and our rectifying section, two knowns, and our stripping section, 2 from our splitter, minus 2 from our feed. We're also going to know from each stream. And then we are going to know the pressure of our condenser. And then the pressure of our reboiler. So this is going to be C, 13, gosh, not 3. 2nr plus 2ns plus 13 minus 2nr minus 2ns minus C plus 2. So C dies. So then 2, 2, 2, 2, 2. So 1, 2, 3, 4. Oh, wait, no, I don't count these. 1, 2, 3, and then 6. Wait. 1, 2, 6. Oh, 6 and then 8. Gosh, I can't do math. So minus 8. So then that leaves us with 5. So 5 degrees of freedom. So then I think this last part is asking, what are the two typical sets of design variables that are specified. All right, so we have 5 degrees of freedom. Oh gosh. Sorry, my thing's not working on me properly. We have 5 degrees of freedom. So then the 5 things that engineers specify is 1, the fact that our distillate product is a saturated liquid. Which in return, here, 1 minute. Okay, saturated liquid. That specifies our QC. Second is we have an optimal feed. Third, we specify the reflux ratio. So our R. And then for 4 and 5, we specify the light key recovery rate. And then the high key recovery rate.